All right. So, hello everyone. Today we continue our course on quantum computing, and today we will discuss in more detail the the Qiskit platform, right? So let me share my screen. Where is it? Here. And then I go to screen number. Where's this one? So do you see my the screen with IBM Quantum, GitHub, and the Jupyter?
Yes.
Okay. Yeah. So yeah, today we discuss this IBM Quantum in more detail, and this IBM Quantum is based on Qiskit, open source software programming kit, which is let me stop my video. Yeah. So yeah, which is open source software, right? And you can find this Qiskit programming tool, for example, with this GitHub, and so this is open source. Here you can check the current version of this Qiskit, the most most recent release, and basically information how to install Qiskit on your local computer. So for example, you can go to, I mean, if you have this Anaconda, then you can go to the Anaconda, it's called Anaconda prompt, and then simply pass this line pipe, install Qiskit, and then the Anaconda will download and install this Qiskit software for you. And I mean, of course, getting Anaconda is like pretty heavy software. It requires several gigabyte, and also, I mean, it's not that convenient sometimes to work in this Python platform. So the people from IBM Quantum, they were so nice to realize this platform for us, like available from any machine, regardless of does the machine has or not the local Python soft install. So basically, last week we started working with this quantum IBM composer, which is simply like a service, right, that allows you to build up any quantum circuits of any kind. You can change the number of qubits in your system. You can put different quantum gates. We have discussed almost all these quantum gates already in the previous lectures. And but the main work actually is usually done not in this composer, but in this quantum lab. So let's go to this quantum lab and let's look what it is. So basically, yeah, let's create another notebook, Python free notebook. And yeah, so as you can see, this page starts with like a simple code for importing basically basic mathematical functions and symbols from NumPy, right? And I mean, yeah, and also from Qiskit. So Qiskit is pre-installed in the system, and from Qiskit we can import this some of the useful some of the useful functions, etc. And we will discuss some of this in what follows. So for now, let's execute this part of the code. And yeah, and let's start with writing a simple code in this Qiskit platform. So the Qiskit is already imported, right? And let's write. So today we're gonna simulate the quantum circuits using two different approaches, two available approaches, using a classical simulator of quantum systems, which kind of mimics the quantum machine, and we will also send the circuit to the quantum to the real IBM quantum machine. And to do so, let's import this function IBMQ. So let's write from Qiskit import IBMQ. So yeah, by the way, if you have access to IBM Quantum Lab, please log in right away and try to like follow me, right? So how many of you have the account in this IBM Quantum? Does anyone have?
I have an account.
Yeah, I have an account, Professor.
Maurice? William? I do have an, okay, I see. Yeah, so yeah, the most of you already have the account. Yeah, so please go to this the quantum lab, right? This quantum lab over here, and simply write the from Qiskit import IBMQ. Right. So then we have this provider. Provider equals IBM dot load underscore account, right? So in this brackets, in this parenthesis, we have to put the, so let me actually copy this line from here, put it here, and here in this parenthesis, in the single quotations, I gonna put the token, right? So I save this page, and let's actually maybe rename this page let's rename. So what lecture is today? Lecture 9? Lecture 9, something like that. Okay. And I save it. So as I save this, I can go back to dashboard. So define, so could you, okay. Now I can mute you, sorry. And also, okay. So please keep your mics muted, okay? So let's go to the dashboard. And here at the dashboard, at the very first page, right, you can find this IPN token, which is generated for you. So if needed, you can regenerate the token, API token, and copy. So this token is like a very long string of numbers and letters, and it's like it's better to keep this token undisclosed, unseen. So let's go back to Quantum Lab. And now I'm going to pass this token in these brackets. So let me stop sharing as I do so. So I inserted the token, execute the line. Let me see. So it's a provider IBM.load account. Okay, make sure you write this. So grammar mistakes. Okay. Yeah, since I already used today this token, I had to let me share my screen back. Right. So so instead of this line, I deleted that line, and I had to rewrote my token. So I wrote IBM.save underscore account, and then simply in this in this brackets, in the parentheses, I wrote, let me stop sharing again, and maybe delete a part of this and start sharing. Okay, so I already executed this line, so my token is already like saved in the memory, right? And I replace this token by this access here. So between these quotations, there will be your token generated in your system. And then I had to write this line here, overwrite true, to replace my like previous token. Since I generated the new one, I had to replace the old one. All right. So then I can call for the account. So I write this IBMQ load account. And this line actually calls the account, right, in the system, actually in the local IBM system, using this token. So this line here, account provider for IBM. So basically this line here shows that I successfully connected to IBM, to the IBM account. All right, so now we can let's actually import everything from Qiskit. So I write from Qiskit import everything, right? So the star means everything. So by this line, I imported all the commands from the Qiskit. And now I'm ready to create my quantum circuit. Right, so my quantum circuit will be a 2-qubit circuit. So I generate the quantum part of the circuit. So it's a quantum register. Two. This two means two 2 qubits. Right, and I also generate, maybe this in the same video, same line. I also generate the classical register. It's a classical register. And I mean, since I gonna measure 2 qubits, so let me make this classical part, classical register, also two-dimensional, right? And and the next line will create the actual circuit. So, circuit quantum circuit with this QR and CR. QR, CR in the parentheses. And I execute this line. Okay, successfully executed. So sometimes when you build up your circuit, you want to actually see what kind of, your result in the graphical representation. To do so, let's import this matplotlib inline command. Inline command. So this command allows you to represent the result in the line as a graphical representation, right? So now we have initiated the quantum circuit, and we just need to put some quantum gates there. So let's start. So let's simulate the circuit that we already analyzed several times. The circuit that that creates the Bell state, right? From the two separate qubits. So what we do, we first apply the Hadamard gate to the first qubit, right? How I do so, I write this circuit, and then dot H stands for Hadamard, and then in the parentheses I have to indicate which qubit I apply this circuit, this gate to. So I applied my my Hadamard gate to the first qubit, right? So the numeration starts from 0, so I have to put 0 here. This QR stands for the quantum register, right? And this is the number of the qubit in the register. So I apply this, and this line tells me that the qubit, the gate was successfully applied. So in order to draw this result, we can call again this circuit dot draw, and in the parentheses, well, let's let it go this way. Yeah. So again, grammar. Yeah. So this is the result. As you can see, I have the qubit 0, qubit 1, and the Hadamard gate is applied to the first qubit in the system. Q stands for the qubit, right? And C0 stands for the classical line. All right. So next gate in this circuit will be control X or CX gate. Circuit dot CX, and so CX gate gets control and target qubits, right? So I have to indicate the my control will be the first one, and the target will be is going to be the second one. So this is the circuit CX QR0 QR1. Okay. So it's successfully applied, and I can draw the circuit. Now I can see, so I have this Hadamard gate first, and then the CX gate as a second one, right? So this is the quantum circuit, and I have to add the measurement, right? The measure to the circuit. So again, it says circuit dot measure RCR. Yeah, in this way, I applied the measurement operation to both qubits. So let's check this out. So I draw the circuit, and I see that indeed I have now two measurement gates at the end of the circuit. So my circuit is ready to be executed, and as I said, today we will try both approaches. The first one is the classical approach, the classical simulator, and the second one will be the completely, like, truly quantum simulator. So let's explore the first approach. classical simulator. To do so, let me call this command for the simulator and give it a name. Well, simulator, let's denote C, classical. Classical. And the name of the simulator we're gonna use is AIR, AER. Dot get backend, and in the parentheses I write ASM underscore simulator. So this is the typical command for the that calls for the simulator. So basically, this AER is the part of the Qiskit that is in charge for the simulation part, and this line here in the name, this is basically just the name of the simulator, this QASM simulator. It allows you to add some level of the noise to your circuit and etc. We'll discuss that in what follows. So let me execute this. Yeah. So this is my simulator, and I'm ready to execute the circuit. So my circuit is named circuit, execute circuit, backend, the backend is simulator C, right? This name for our simulator. Execute the line. It's successfully executed, but now I have to write the part of the code that calls for the results of my simulation, right? So let me denote this. Let me name this as a result C. Execute circuit backend simulator C, and let's turn this to a result. Parentheses. Okay. So we gave the result. We turned the execution line into the result and assigned and named the result C, where C stands for the classical simulation. Classical simulation. So now let me download this visualization from Qiskit .tools visualization import plot histogram. Okay, so it's imported, and now I can use this Instagram representation to show the results of my simulations. How I do so? By this line plot histogram, and then the command says result C, right? And get then underscore counts. So the counts, you will see in a second what it is. And the name of my circuit, which is just circuit. Circuit. Okay. So this is the this is the result of the simulation, right? So by default, the number of simulations here is how many? 1024. This number, and I can change this number by changing this line here. So I can attribute another well, the attribute, right? This number of shots. Let's start, for example, from 5, very small number. And I also want to combine to merge these 3 lines. So merge them. Right, and I execute this. So as you can see, for just 5 simulations, we've got 3 realizations gave us state 0 and 0, and other 2 gave us just 2 realizations of 1 1. So we can simulate this once again, and this is supposed to be so probably, yeah, since we didn't add the noise to the system, it gives us pretty much the same. Oh no, yeah, so it works this way. So for just 5 simulations, yeah, the output is arbitrary, so as you can see. But if I increase this number of shots, it's just the number of executions, right? So the system takes this circuit that we gave it and simulates the circuits multiple times. So we started with 5, now I simulated 50 times. As you can see, this the difference between 2 realizations became smaller. I increased this to the 500 and it became even smaller, 5,000. So now they come like almost the same. We can put 50,000. They come so the dispersion between the 2 states like is vanishing as I increase the number of simulations, and this is for 500,000. So the difference is like almost negligible. Yeah, so this is how we simulate this particular circuit, and as we discussed, so this circuit, this let's say this blue part, right before the measurement, this part of the circuit creates the Bell state, which is entangled state with ultimate entangledness, right? And when I measure this circuit, I expect to get either 0 0 state, because if I measure, for example, the first qubit, and and I can detect either 0 or 1. But since these qubits are entangled, I know that my second qubit also will be in the same state, either 0 or 1, depending on the state of the first one. This is the quantum entanglement, like the state of the first qubit affects the state of the second qubit, or actually the result of the measurement of the first qubit defines with 100% certainty the state of the second qubit. That's why we can get either 0, 0 state or 1, 1 state. And in the theoretically like perfect scenario of qubits with 100% fidelity, when they like work very good, right? Very like close to theoretical perfect case. Then I supposed to have the balanced like symmetric realization. 50% of the counts go to the 0, 0, and another 50% go to state 1, 1. Of course, any system has the noise and accuracy, etc. That's why when I decrease the number of simulations to a very small number, I have this very large dispersion, but in reality, my number of simulations is around 1,000, and this dispersion is very small. So this is about the classical simulation of quantum circuits like this one. That takes into account the effect of quantum noise, right? So in contrast to the realistic quantum machines in this classical simulator, we can simulate systems basically of many qubits, right? Up to some certain limitation. Do you have any questions at the moment?
No question, Professor.
Oh.
No problem.
Very good. Okay, so then let's go to the simulation on a on a real quantum machine. Then so simulation. I just hope that IBM is not that busy today, so we can execute something on their machine. Right. So so first of all, let's save this work page and go here to check what resources are available right now. So this web page compute resources. So this web page shows us the 14 items which are basically existing quantum processors that are available like right now for execution of our quantum circuit. We will discuss the parameters in what follows today. The most important for now is this column, qubits, right? So if I arrange these numbers from least to the largest, you can see that we have multiple choice of quantum processors with 5 qubits, 7 qubits, 32 qubits, 63, etc. And of course, the more qubits the processor has, the more complicated circuits we can simulate. by now our circuit is 2-qubit system, so we can easily choose any of these 5 or 7 qubits machines, right? Just, I mean, usually they have the smallest number of pending jobs, because like people mostly interested in simulating quantum problems, tasks on a big quantum computers. So usually these processors are least busy, right? So as I can see right now, this IBM Oslo has the smallest number of pending jobs, and we're gonna take this one for our simulation. So IBM Oslo. Let's go back to Quantum Lab. Go back for Quantum Lab. And so first of all, we need to call for the provider, which is IBM, right? So provider, our provider is IBMQ, IBMQ. So as you can see, Qiskit, I mean, is a general system. You can use this system to call for any provider existing, and of course, up to date, IBM is the only company that provides this quantum computation facility, open access, and completely for free. So we don't pay a single penny for using their quantum machines, at least like today, right? So they doing that, they try to engage more and more people, students, researchers to the field of quantum, and also like of course use their platform. Right, so I call for provider, which is IBMQ, and in this provider I write get underscore provider, and the name of my provider is IBMQ. Let's execute this line. Okay, so now we have this provider. And now we have choose the quantum computer. So write Q computer. Provider. So these lines like pretty much the same when you write any quantum code using Qiskit. So the provider, then get, then underscore backend, and and the name of chosen processor. So what it was, I just forgot. And of course, let's check, maybe it changed. So let me, yeah, so this one, as you can see, so now this another processor, this IBM QE2 has the least number of pending jobs. So let's choose this one and go to the quantum lab. Put this name of the processor here and execute the line. So then I call my job, right? The job, I mean, the name of the job. Let's name this job Q, for example, the quantum. Execute. The name of my circuit, which is just circuit, and then back and the name of the computer, which is QComp in my case, execute. Okay, so this job is now sent to IBM quantum computer, and now it is in the line. But usually I want to see like the process while my job gets to the execution, right? So let's let's write this this line of the code for the job monitor. So from Qiskit Qiskit.tools monitors import job monitor monitor job monitor Qiskit tools monitors from Qiskit.tools monitor, sorry, yeah, monitor, and let's call this function job monitor, and the name of the job, which is job queue. Let us see. So as we can see, our job is in the line, and we have like 15 jobs ahead. So my guess, since this processor is just 5 qubits, so I guess it will be executed maybe in 5 minutes or so. So let's wait for that, for the result. Meanwhile, we can save this and go, for example, to the compute resources, and let's look at the processor that we use. So this IBM Q, I'm not sure what kind of processor is this. Any information? IBM Q. I hope that I can like see how this processor look like. So for the characteristics of this processor, you can simply go click this line, yeah, and see the parameters and specifications of this processor, the architecture of the processor, basically how the CNOT gates realized, then the number of qubits in the processor. Then this quantum volume. Quantum volume is a very important parameter. Quantum volume basically equal to the number of qubits that you can execute times the number of layers, right? So for example, in our circuit, we have 2 qubits, basically these 2 quantum lines, 2 registers, right? And 2 layers. When quantum computer executes the quantum circuit, it goes from left to right, starting from the very first qubit and ends at the very last qubit, which is usually the measuring qubit, measure qubit. And as it goes from left to right, it does the program as a slice, right? As the slice. So the first slice is the first qubit. The second slice is all the second qubits in the circuit, then third, fourth, etc. And so the quantum volume is simply the product of the number of registers. In our case, it's 2, by the number of slides. In our case, this is also 2. So in our case, the quantum volume, roughly saying, is just 4. And using these qubits, using this quantum processor, you can simulate easily the circuits with the quantum volume of 16. So if your circuit, for example, is a 4 register, and then you can put 4 slices there, 4 layers. So such a circuit can be executed using this processor. So let's go back and see if our job is executed. Not yet, and let me call this once again. You can also see the progress at the very first page, which is dashboard. But yeah, it doesn't allow me to save the page, so let's wait for a while. Do you have any questions?
No, Professor.
No, Professor.
Very good. So it really depends on how the quantum computers like busy. Sometimes this execution time could be maybe just 2 minutes or 5 minutes. Sometimes it's longer, depending on the number of pending jobs, of course. Yeah, at this moment, also let me, while we wait for the result, right? Let us discuss this ChatGPT, right? I mean, in terms of the quantum simulation. So, yeah, apparently, even at this stage, this ChatGPT is kind of interesting artificial intelligence system. It's pretty helpful in generating at least simple quantum circuits, right? And it's interesting in 2 aspects. So first of all, we can write something like I don't know, write Qiskit code for generation of a Bell state, for example, right? And what it basically does, it does basically the same, right? So it also imports this Qiskit, quantum circuits, AER, which is the name of the simulator, right? And this execution. function. It creates the quantum circuit with 2 quantum and 2 classical digits. Then it creates the Hadamard gate, the first one, then CX gate with control to the first and the target to the second, right? Then the measurement, and yeah, then it calls for the simulator and simulates the result. So this code looks pretty pretty correct. let me check if, yeah, so meanwhile our job is done, but before we check the result, let me go to the Jupyter, right? I hope that any of you already know how to install and launch Jupyter, or you can use any other Python soft to run Python codes, right? You can create the new Jupyter page, copy paste this code here, and try running, hoping for a good. Yeah, so yeah, as you can see, again, we obtain basically the same result. So 50%, roughly 50% of the first qubit in the, I mean, of the first, roughly 50% of the simulations end to the state 0, 0, and another 50% end to the state 1, 1. And this code was generated in this Qiskit, or in this ChatGPT, right? And you can modify this, right, as the, for example, show result as a histogram, for example, right? So it modifies the code, also imports this plot histogram from the Qiskit visualization. Basically, what we just did, right? And you can use this code for simulations and showing the, yeah, the count. So the same, exactly the same result as we obtain here, right? As you can see. So this approach works pretty okay for at least like simple quantum circuits, because, I mean, of course, you know that ChatGPT was trained based on the available information in the internet, right? And this topic of Bell state generation, of course, was discussed in thousands and thousands of papers, pages, etc. And of course, it generates this part pretty good. But if you ask him to add something more sophisticated, I don't know, for example, add noise generator for example, something like this. So I'm trying to add controlled noise to my circuit. So it also generates a code which, like, at the first glance, it looks like it makes sense. And if you execute this code, so usually it gives me an error. Let me see. Yeah. So it always something that you have to fix here. And I mean, sometimes it's just a little correction. Sometimes you need to rewrite some part, but in general, this ChatGPT creates a very good draft for quantum simulations. Okay, we will discuss this point. No, actually, let me tell you the second very important point. When you actually would like to use ChatGPT for simulations in quantum. So ChatGPT solves pretty good the opposite, the reversed problem. So our problem now is like, oh, we have a circuit, and what's the output, right? What is the result of simulation or execution of the circuit? But what if I ask, like, if I give you a state, some, for example, a state like this, it doesn't matter, like something like this, right? So this is also entangled state, and you can write like give me the quantum circuit that generates this the state 000 plus 101, right? And usually it solves, again, just for maybe 2-3 qubits, it solves the problem nicely. So why I mentioned this? Well, in your homework, in your third homework, you have this task to suggest a quantum circuit that generates a particular state there. So you are welcome to use Qiskit or ChatGPT to generate the quantum circuit. I mean, of course, you should validate your solution. You should demonstrate. My suggestion: demonstrate analytically and using Qiskit the result of the circuit. The result that, I mean, the result is exactly the state that you are after. All right. So meanwhile, our real quantum simulation using IBM quantum computer is done. Sometimes this name Quito is just like a place somewhere. So maybe this Quito is like this processor is located somewhere in Japan, or I'm not sure. I don't know. Don't know that. But yeah, so the job is done, and let's actually check the results, right? So for the results, let me write this result Q. So the result of execution of quantum approach, right? And it's a job Q. This is the name of our job, and then call for result. Call for result. All right, so we gave the name to the result, and let's plot the result again as a histogram. With the name of our result, which is result Q. Then we call for the function get underscore counts, and the name of our circuit, which is just circuit. Done. Yeah, so this is the result of our quantum simulation. As you can see, I didn't pay for this simulation a penny. That's completely for free. You are able to choose between 14 quantum processors. Oh well, some of them will also look at the list. Some of them are not the uh, like truly quantum processors. It means that some of them have 1,000 qubits, but they are not fully entangled. So the complete list of processors is around 10. So still, anyway, you can choose any qubit from the list of 10, and that's completely for free. And the result, as you can see, the result is a little bit, the different in a very important aspect. So the result of the quantum of the classical simulation that mimics or pretends it works as a quantum, right? It gives you just two states, two realizations, 0, 0 and 1, 1. Why? Because this simulator assumes that your C0 gate, which creates the entanglement, is completely perfect, right? So it creates only 0, 0, 1, 1, and nothing in between. So no other states, 0, 1, 1, 0. In reality, of course, the quantum processor is not perfect, and we have chosen, I guess, the one of the oldest ones of the processors. So it still generates the state 0, 0, 1, 1. Like, you can see that these two peaks are the highest, and the portion of mixed states 0, 1, 1, 0, which means that this entanglement is not perfect. So it's not full complete entanglement. It's a entanglement with some portion of mixed coupling between the qubits. So this is kind of the perfect case. In the perfect case, these two middle spikes would be like around 0. The less, the better. And so people introduce the quantity that describes the performance, the quality of the quantum processor, and compares it with the perfect, theoretically perfect case, right? And we call this fidelity. So as we can see, fidelity here would be like around maybe 90%, which is still very good for taking into account that the processor is like old and outdated. And if I would choose another processor, this result would be better. And of course, it degrades as I add more and more circuits, the gates to my circuit, right? So do you have any questions before I proceed?
No question, Professor.
Okay. So Maurice, your mic like is very noisy. I'm not sure why. So I muted you. So yeah, if you have no questions, let's proceed with from scratch. So let's go to Quantum Composer and to see what kind of functionality this composer provides us. So we already use this composer for constructing simple circuits, right? And in your homework number 3, you've been asked to simulate some sort of a circuit using this composer. But now let's compose some like a more complicated circuit. Let's put some, for example, X here, X here, some, for example, Z here, then Hadamard gate here, the control X here, for example, Hadamard gates here and here. Then would be something like another entanglement between the first and second. Then we can add this swap gate, which swaps the first and second. Then, for example, this S gate to the third one, right? Then we never discussed this one, but CCX gate, also known as TOEFL gate. So this is very like similar to the CX gate, C not gate, but it gets another. So this is 3-qubit gate. It gets another portal. That's another node here, and basically the result, as you can see, the two are control, and the third one is target, and the state of the target depends on the state of two control. Basically, the target is changed only when the state of the both control are equal to 1, right? So yeah, so that's already pretty complicated circuits. We can add more, and I want to draw your attention to this Qiskit program on the right. So when I add new gates to my circuit, this code is gets another line, right? So it automatically rewrites the code to that corresponds to the circuit. So let me remove the fourth qubit and make the classical line also 3-digit. All right. And this is the like classical result, like perfect scenario. As you can see, it's just 50% probability of 0, 1, 0, and another 50% of probability finding the state in 1, 0, 1. And finally, I add the measurements here, measurement gates, right? Yeah. And as I add this measurement, the program assumes that like you simulated your circuits many times. And as you can see now, the probability became smaller. I mean, it's a little different. So now in this particular case, in this particular realization, the probability of finding the state 0, 1, 0 in the it's 49.2%, and corresponding 50.8% for the 101. So now you can inspect the circuit, clicking here. You can start from the first gate in the system and go slice by slice. So as we discussed, so these 3 qubits here represent the first slice of the circuit. Then we have the second slice, third, fourth, and as I go slice by slice, the program gives me the result of execution of this circuit. Right, and then the main point of having this quantum composer is that it creates this Python code for us. So we don't need to write all this, add the circuit X, add another X, then add another Z, then Hadamard, then CX. So it's written like automatically. And now I can take this code, simply clicking open in Quantum Lab. I can take this code to the Quantum Lab. So let me change the name of this to, I don't know, like more complicated circuit. More complicated circuit. So now if you execute this code, all right, it returns this quantum composer here and gets all these gates and the circuits to the memory. So now at this moment you can actually change the circuit simply clicking here, this create a cell and synchronize the circuit Qiskit code in output. So you created another cell that copy just this program here for the circuit, right? But now you can change this circuit right here. So you can use this cell as a composer and add new gates, and these gates are automatically applied here and show up. So you can execute this one, and yeah, so you got this very, not very, but like more sophisticated quantum circuit. So now, yeah, do you have any questions?
No,
Okay,
Professor.
so all right. So if not, let's again run the classical and quantum simulators. So run classical simulator, right? So let me start. Yeah, I don't have it here. So let me start with import of everything from Qiskit. From Qiskit import everything. Just in a case, and then let's call for simulator. Let's name the simulator classical complicated, for example, right? So it's equal. Let's use the same simulator air. Then we get this backend, and in the brackets I specify the name of the simulator, which is KISM simulator. Executed. Not executed, the code for the simulator, and then for the result classical complicated, we execute the circuit. Our circuit has name circuit again, Okay, so let's just copy paste this circuit name here. Then backend simulator CS, classical, complicated, right? And yeah, and then let's turn this to result. Okay, so now just in case, let's import the histogram method of representing the data. So from Qiskit tools visualization import what histogram. Very good. And yeah, as a result, let's plot the histogram. Result CS CC actually dot get count counts so the name of our circuit. Oops. The results. I see. So it was result res c. Okay, so this is the result of simulation of our like more complicated quantum circuit. As you can see, this simulation is run like almost instantly. So that it takes just a fraction of a second to simulate even such a circuit. I mean, using this classical approach. So now let's go ahead and run all quantum simulator using IBM quantum processor. How we do so? Again, from Qiskit, I import IBMQ. This function IBMQ allows me to send my project to the IBM machine, right? So then I have to add my token, right, to the program. I do so by IBMQ save my token account and here in the quotations I will put my token that I will copy and paste from the first page, right? And I just write this command here overwrite to like to overwrite the token if I like change that, so it will work anyway, right? So let me write the third line here. IBMQ load account. So these 3 lines will create the account call for account at the local IBM machine. And now I will send this page, and I will go to the first, to the to the dashboard web page to copy and paste my token here. So let me stop sharing for a moment. Go to dashboards, copy IP token, and go back to Quantum Lab. And insert this token here and execute the line. Yep, done. Okay, so yeah, I already connected to the IBM system with my token, right? And which is a unique password to access the local IBM, actually remote IBM quantum machine. And now we need to specify the particular provider, which is IBMQ. Get underscore provider, and the name of the provider, guess what? IBMQ. IBMQ. Cute. Looks good. So the next line is choose the quantum computer. Quantum computer. Quantum computer. Provider gets underscore backend, and the name of a computer. Again, let's choose the least busy one. Still this one QETO. Let's go for another one. This IBM BLM. Let's go for this for another computer, for another processor. And put the name here. Right. Okay. So now let's create the job with the name job. Let's job quantum complicated. Let's call it this way. Execute. The name of the circuit is just circuit. Maybe I should change that. Yeah. Circuit backend. And the name of my computer, which is QC. QC, all right. And again, I call for the job monitor from Qiskit. From Qiskit dot tools monitor. I import job monitor, right? And import, and I show up this job monitor for the job with name job QC. Okay, so the job in the line, and I have just 12 jobs behind before me. in this line. So while this job is getting executed, let me return to this circuit here and make maybe a well, important note here. So as you can see, the result of this complicated circuit, right, which gets how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16 gates, right? 16 gates or 13 gates plus 3 measurement gates. The result of this simulation is like very simple, just two states, two realizations. So my circuit can evolve either to state 001 or state 110 after the simulation and after I measure it. So basically, for example, if I measure state 0 in my third qubit, right, this 0 here in third qubit, then can I get this second state? No, it's not possible, because if I detect 0 in the third qubit, then my second and the first qubits must be, I mean, in the theoretical case, in the perfect case, must be in 0, 1. Again, this is the quantum entanglement. And vice versa, if I measure this third qubit in the state 1, then my second and first must be in the state 1 and 0. Yeah, so this is the quantum entanglement, right? And another point is that the result is pretty similar, and I bet you can come up with another circuit which is much shorter and much more optimized to achieve the same result, right? So like simulating a circuit with 16 qubits is not a, I mean, like more qubits you add to your system, the larger noise, less fidelity of your circuit. So what people do in this area, they really like try to optimize, not only come up with a circuit that is doing something useful, but also optimize the circuit for the smallest number of qubits to achieve the same functionality. And this is kind of important task today, this quantum computation task. So we still have 11 jobs. So as you can see, it takes some time. Meanwhile, we can check out what this IBM BLEM quantum processor means characteristics. We can go here. BLEM. Yeah. So it has a similar architecture to the previous one, also 5 qubits, and the quantum volume is also 16. These are the gates that the processor supports, right? So basically all the Clifford gates. Oh, apparently I already run in this account. I already run 3 jobs on this processor. So as you can see, this C0 gate is kind of the most important one because it's a gate that creates entanglement. So all the quantum computation information, all the based on the creation of entanglement, and the better your entanglement, the larger fidelity of your circuit is, and what people do in terms of like to measure like or estimate the fidelity of your circuit, they measure for the C0 error, which gives you an idea like how noisy the C0 gate is, how much mistake or inaccuracy this particular qubit brings to the system. In what follows, maybe next time or in a couple of weeks, we will briefly discuss how these single qubit gates and 2 qubit gates work. The operation principle is like the concept is very easy. Of course, the implementation in the lab or in a realistic processor is very difficult task. That's why like thousands of people work in that area trying to realize a better quantum computer. A very important point here is that this single qubit gates, 2 qubit gates, they get this quantum coherence, right? The quantum state, and that quantum state that lives there for a very short period of time, roughly 10 milliseconds. So like when you have a qubit, you excite a quantum state there. Typically, this quantum state lives there for several milliseconds. Oh, they actually put this information here. So this is characterized by 2 times, this T1 and T2. So T1 and T2. And this times, the shortest one is this one, T1, right? So this is just 98 microseconds. Right, so it's a very short period of time, meaning that, right, so like when you excite this quantum state in this qubit, in this circuit, like after just a few moments, just few portions of a millisecond, the quantum state is gone. So you cannot run your simulation for a very long time. That's why we have a finite quantum volume. If we always can put more and more qubits there, and more like register, but the number of slices is finite. I mean, of course, it depends on architecture, how it actually works, all those things, but in general, you are very limited in terms of this number of slices, the number of layers of qubits, because your time of execution of the quantum algorithm is very, very limited. Okay, let's and these two are very similar, right? So the number of qubits the same. These are 2 qubits that we use today, this Quito and Billiam. The quantum volume is the same. This CLOPS, this is another number that characterizes I don't remember what it is exactly. It's it's associated with some like reconfiguration of the circuits. I don't remember exactly. It's 2.5 thousand it's called circuit layer operations per second. So it's apparently this processor can do 2,500 circuit operations per second. Of course, it depends on the operation frequency of the elements, and these qubits are superconducting microwave qubits, right? So they work at the frequency around 5 gigahertz, and 5 gigahertz, what it is? It is 5 billion oscillations of the field per second. 5 billion, right? Yeah, and yeah, the processor type actually this one, this Falcon R4T. So if you Google it, you can actually, hopefully you can see what kind of processor it is. All right, and let's go to the quantum lab. And see, no, it's still running. No, so it has been successfully run. All right, so just let me repeat what we just done, right? We created the quantum circuit using this Qiskit, and then using the unique like ID, which is called this IBM token, API token, we sent our quantum circuit to a real quantum computer, which is located somewhere, maybe somewhere in Europe, but most likely here in US. And a real quantum computer that has been built by many people, fantastic people, researchers, engineers, etc. This quantum circuit has been executed for us for free, and that's actually like cool. Like here, sitting in Miami, I can send something to somewhere, run this quantum algorithm, and create quantum entanglement. That sounds very interesting. I like always fascinated by that. Like you create quantum entanglement sitting at home. Okay, so yeah, the result is I mean, the job is executed. We just need to get the result, right? So let's name the result let's call this Q C. Anyway, so it's job. The name of our job dot, let's go for the actual result, and let's plot the result as a histogram. Then the first parameter is the name of our job. Oops. No, the name of our job. Then I do get. I get counts, and the name of my circuit is just circuit. On the circuit. Okay, so this is the result of simulation of our sophisticated quantum circuit containing 16 gates, right? The using real quantum IBM computer. The simulation itself, we can check that the simulation itself takes just a portion of a second. But of course, the main time is like while you wait in the line. And again, so the perfect case when I have no cross talking between the qubits and between the gates, I expect just two realizations, 001 and 110. In the quantum case, I get still I have like reliable, easily like seen two spikes at the states 001, 110. But on top of that, I have this kind of noise for the other states, 000, 010, 111, 100, etc. And this is kind of a mistake, right? This is kind of a noise in my system, but still, even for such a complicated circuit, I get a very good result. I guess the fidelity of this result will be also around 90%. But comparing to the previous case, where it was here, right? I saved this one. So comparing to this case, here I had only like four gates, two actual quantum gates, and the result was, also kind of 90% of fidelity. In this case, the circuit is much more complicated, and the fidelity is roughly the same. So Qiskit provides you with all these tools. You can calculate fidelity. You can calculate basically everything. You can represent this data using Q sphere, which is analog to the block sphere of the single qubit, as you remember, etc. Yeah, so and maybe as a very last example, yeah, before I go ahead, do you have any questions? Okay, if no, let me maybe finally simulate this GXZ state. So let me create a new notebook. A new notebook. Remove these two lines. No, actually, let's also use the composer. So I everything here. Go to the quantum composer and create this GXZ circuit. So we discussed many times this golden 2-qubit circuit, right? Which is Hadamard gate plus the CNOT gate or CX gate. So this circuit creates the entangled state, which is called Bell state. Right, Bell state. But what if I want to create a more like also the analog of this fully entangled state, but for 3 qubits? So I add another qubit, and to do so, I just add another CX gate between the first and second qubit. Right. So you see this evaluation, evolution. Before I apply the measurement gate, the my simulation now is like completely perfect. I get 50% of probability of state 000 and 50% for 111 state. Meaning that if I measure, for example, the first qubit and find this qubit in the state 0, then I'm sure that the other two qubits are also in the state 0 and vice versa. For example, I measure the second qubit in the system and find it in the state 1, then I'm sure, like 100% certainty, that the rest of the qubits, the second and the third and the third, also in the state 1. And this is called GXZ circuit. So it's kind of a generalization of the Bell state circuit. And similarly, I can add another qubit and entangle it with the previous one, and it creates 4-0 state and 4-1 state, and etc. Right. So we can create this perfectly entangled states between any number of qubits, any number of qubits. Yeah. So that's it for today's lecture about the Qiskit programming. I will assign a homework for you to execute a quantum program using, these two approaches, the classical and the quantum one, using IBM quantum machine. And let me stop the sharing and recording, and then I will say a few words about the midterm exam.